Hello everyone, in this video I'm going to go over some of the proof questions from the practice test 2. So let's go ahead and look at number 10. We're just going to do part A. So consider the set M, which consists of all 2x2 matrices with real entries whose lower left entry is 0. So they're like upper triangular matrices. Use the typical matrix addition and multiplication operations and prove that M satisfies axiom 4. So for this, I would just go ahead and note what axiom 4 is, because I do not have these memorized, even though I've taught this a bunch. There's just too many of them. Let's see. So axiom 4 is, here it is. Okay, ring axioms, additive, identity, or zero element. Okay, so we need to show that there exists a zero element. Oops, sorry, scrolling around too far. Okay, back to number 10 here. So show that M satisfies axiom 4, which is this. So additive, identity, or zero element. There exists a zero element in R such that for all A in R, A plus 0 equals A, which equals 0R plus A. Okay, so this is not too bad for matrices. The zero matrix is, if we're just doing regular matrix addition, it's just the matrix of all zeros. Okay, so we're gonna claim, we're gonna assert that 0 sub M is gonna be zero matrix. Oh, how do I insert this? Hold on. Equation. We need a 2x2. I don't know how to do the keyboard shortcut for the 2x2, so I just insert it from there. Okay. So we're going to assert that this is the zero element, and then we have to prove that it actually satisfies the properties here, such that for all A in R, so for all elements of the ring, it satisfies this three-part equation. So what we need to do is, for proving this part, the for all A in R part, we need to let ourselves take a random element of our set, M, which is 2x2 matrices with real entries, where the lower left entry is 0. Okay, so we're going to let's call it capital A since it's a matrix. Let A in M. Then, all right, so we know that the form of A is going to be like this. It is a 2x2 matrix where the lower left entry is 0. And we don't know anything else about the other entries, so maybe I'll just call them I don't know, X, Y, and Z. And those are supposed to be real entries. So I'm going to claim that X, Y, and Z are real numbers. Okay, and now what I need to do is I need to show that our 0M and capital A satisfy this equation right here, the three-part equation. Okay, so to show that they satisfy it, I'm just going to simplify this part by itself. I'm going to simplify this part by itself. I don't really need to do the middle part because that's just A. It's already as simple as it gets. And I'm going to show that they're all come out to the same thing. All right. So then A plus 0 sub M is going to be, so I'm just going to paste in what these things are. It's that plus that. And that's going to come out to, well, you guys can see yourselves, right? Okay, it just comes out to be A again. And you know what? I could even just use the fact that matrix addition is commutative at this point. I don't really need to do the other side because matrix addition is commutative. So I can just claim, since matrix addition, actually all ring addition is commutative, but at this point, we're still in proving axioms, so we haven't necessarily proved that it is. If we were working with another random ring, you couldn't necessarily assume that the addition was commutative unless you showed that it was. But in this case, since it's matrix addition, we know that it is commutative. So this will be the same as 0M plus A. And both of those are the same as just A. So we have shown, what have we shown? We did this part right here, but I'm just going to rewrite it with capital A's and M instead of R. So that's it. We have shown axiom 4, which was this. So I would not necessarily include writing that out in your actual proof, but that's just like some background information, like note to self. This is our goal here. All right, so let's look at the next one. We're going to do another axiom. So consider the set V, which consists of all complex numbers a plus bi, such that a squared plus b squared equals 1, where I is the imaginary number square root of -1. Note, this is not the same as the U set that was in the previous set of questions, the non-proof questions. So in those questions, we had a 2 right here. This is a 1. And for these questions, we're going to use the usual addition and multiplication operations for complex numbers, which are the same as the ones for the real numbers. So we need to prove that V satisfies axiom 6. So I'm just going to go look for what axiom 6 is, so I know what I'm trying to prove. And here it is right here. It's closure for multiplication. Okay, so I'm going to paste that up here so I know what I'm trying to prove. Okay. So again, this is going to be like a note to self kind of, this number here. Okay, so note to self, that's what I'm trying to prove right there. So in order to prove a for all statement, I need to make this part into a let statement, and then I need to show this part. So I'm going to start off with making this blue, first of all. I have a bluing macro that turns things blue. Okay, anyway. So I'm going to start off by letting A and B... Actually, I don't want to call them A and B because A and B were already used in the problem statement up here. So let me call them X and Y instead. So I'm going to let X and Y be in this set V. And then my goal here is, like, we will show XY is in V also. All right, so what do I know about X and Y being in V? Well, all I really know is that they have this form. They're complex numbers, so they look something like this. Something plus something times I. And I guess I forgot to kind of mention this, but like the A and A plus B here are real numbers. And they satisfy this equation right here. Okay, so I can say that X equals A plus BI and Y equals, I don't know, C plus DI, where, oops, A and B satisfy the equation, so A squared plus B squared equals 1, and C squared plus D squared also has to equal, oops, not the D, C to the 2 plus D squared equals 1 as well. Okay, and so then what I need to show is just when I multiply X and Y together, whatever I get when I do that also satisfies this equation, real part squared plus imaginary part squared equals 1. Okay. So then I'm going to do x, y. I'm going to multiply these together. So it's a plus bi, c plus di. And so I'm just going to FOIL this out. So it's first, outer, inner, last, bd squared. Okay, and then when you're simplifying this, you want to group the real parts together and the imaginary parts together. So AC is real, but BDI squared is also real because I squared is -1. So you replace that with -1. So the real part is going to be AC minus BD. Okay, and then the imaginary part, the imaginary coefficient is going to be AD plus BC. That's times I. Okay, so when you're submitting those to the testing equation up here to see if they can gain membership, to see if XY has membership in V, the things that you're squaring are this real part here and this imaginary coefficient here. Okay, so then we can check if this is in V by doing, okay, so we're gonna square and square, and I'm just gonna paste these things in here. We're gonna square that. And we're going to square that, and we're going to see if it comes out to be 1 or not. So a little bit tedious, but this is what we have to do. Okay, so I'm just foiling again. This is going to be, so first, a squared, c squared, oh, and then it's, so it's -2 times a, b, c, d, and then plus b squared, d squared. All right, so that's the first one. And then foiling the second one, let's see, so first, then we have 2 times each of them. And that's going to be a, b, c, d again. And then the last part is b squared, c squared. Okay, hopefully this simplifies, because it's kind of yucky. I see that -2 ABCD and +2 ABCD are going to cancel out, so then I'm left with a squared, c squared, b squared, d squared, which I'm not in love with, a squared, d squared, b squared, c squared, and you're like, yuck, how is this going to possibly simplify to 1? But remember, we have these assumptions up here. A squared plus b squared is 1, and c squared plus d squared is also 1. So at this point, you could, like, I don't know, maybe solve this for a squared and substitute in for a squared down here. Or you could start trying to, like, simplify this. As you see, there's 2 parts that have a squared in it. So if you factor out a squared from those 2 parts, and then you could factor out b squared from these 2 parts. Okay, so let's do that. So the 2 parts that have a squared are c squared, d squared, and then the other 2 terms have b squared multiplied by both of them. And so you also have c squared plus d squared here. And in fact, if you look at what you've got here, now you can factor out c squared plus d squared from both of these. And you actually have this. None of this should be a surprise to people who've taken complex analysis. So this does actually turn out to be just 1. Okay, so that means xy is in B. It did pass the membership test. Okay, so that proves axiom 6. Again, we were just trying to show that the product there was in the set. Okay, let's move along to number 12. So in this one, we have kind of an interesting set. I'm not sure if you guys have ever worked with this set before, but this is the extended real numbers, or one version of the extended real numbers anyway. So it's real numbers, and we're also including these 2 symbols, infinity and negative infinity, as part of the set. And so the operations here are regular addition, but there is an extended rule for how you handle addition with infinity. So if you have to add infinities, anything plus infinity, except for negative infinity, is infinity. And anything plus negative infinity, except for positive infinity, is negative infinity. And then if you have to add the 2 infinities together, you get 0. I should have, I guess, worded all this a little bit better, but it's basically like kind of what you would expect to happen when you add infinity or negative infinity, except for this part. This part is totally whack, because that is not how L'Hopital's rule works. When you do something that whose limit is infinity plus something whose limit is negative infinity, like in calculus class, you can get anything. But for this particular problem, I'm just saying that you always get 0. Anyway, and then the multiplication operation is the same wacky one with the star symbol that we saw before. And the 1/a part is standing for regular real number division, except we have these extra extended rules where 1/0, now it's not undefined, it is defined as infinity. So it's no longer undefined. We defined it. And same here for positive and negative infinity. If you put either of those in the denominator under 1, you will get 0. So these are some kind of weird, wacky rules, but what you find is that you can actually get satisfaction for a lot of these axioms when you extend the rules like this. So let's look at axiom 11. I'm just going to scroll down and grab it. So axiom 11 is zero product property. So for this one, you do have to already know what the 0 element is, but since addition for this problem is defined as just regular real number addition with the extended rules for infinity, we can tell from that already that the 0 element has to be regular 0 for the regular, addition in real numbers. Okay, so this is not part of the proof, but this is note to self. This is what we're trying to prove. Okay, so make it blue. All right, so what we need to do here to start off the proof is turn this for all into a let. And so we are going to let A and B be elements of E, which is our set. And then we have an if-then statement we're trying to prove. So we're going to go ahead and assume the if part is true. So assume A, and now our multiplication operation is called star. So we're going to write it as A star B equals 0 sub E. And we do know, I think on the actual, this was part C, so I think the part where you figure out what 0E is was like a previous part. So that does have to be 0. And then we will show, so we're going to show this. So either A is 0, I'll just replace this with like regular 0, or B is 0. Okay, so how do we do this part? Well, we have to leverage our assumptions, and the only things we really have are this equation, and we have that A and B are elements of the set. So either A and B are both real numbers, or maybe one of them is a real number, the other one could be one of the infinities, or they could both be infinities. We don't really know, so I'll hold off on using that assumption for now. Let's try using this assumption, the equation. Okay, so since A star B equals, I'm just going to, instead of 0 sub E, I'll just write regular 0 since that's what it is. Just going to plug in for what the star thingy is. So I'll just paste this in here. And I'll make it blue. We know that that equals 0. Okay, so at this point you're like, wait, if I just multiply both sides by 1 over A plus 1 over B, then I get 1 equals 0. Well, no, wait, because that's for regular real numbers, but we have these wacky extended rules. Remember, we do have that 1 over something can equal 0 in this situation. Normally with just real numbers, 1 over something cannot equal 0, but we have this 1 over plus or minus infinity can be 0. Okay, so what we actually have right here is that tells us that the denominator, this part, has to be either plus or minus infinity. Okay, so since 1 over real number cannot be 0, we conclude that we must have this situation. Okay, so that tells us that the denominator, we have either 1 over A plus 1 over B is positive infinity or negative infinity. Empty or negative empty. Okay, so one of these two things. So we could do like a case 1, case 2 type of situation. So let's do case, oops, not in equation format. So let's do case 1, this one. Okay. And then we can make case 2 be this one. Okay, so if case 1 is 1 over A plus 1 over B equals infinity, remember our goal here we're trying to show is that either A or B is 0. And so now we have to ask ourselves, how can we solve this for A or B? We didn't really get any rules about like multiplying both sides by anything, but we do know when a sum turns out to be infinity, that's the situation where one of the things you were adding was infinity. Okay, and if the sum turns out to be negative infinity, that means one of the things you were adding was negative infinity. Okay. So this implies either 1 over A or 1 over B, or maybe both, was infinity. Okay, and actually same deal down here. I'll just copy and paste this. This one would imply 1 over A or 1 over B was negative infinity. Okay, so now we have to solve for what A or B was. Remember, 1 over 0 is defined to be infinity, and that's the only time we know of that 1 over something is infinity. So this 1 over A or 1 over B being infinity would imply that either A or B was 0. Which is exactly what we are looking for. And the same thing is true down here. Actually, you know what? For the second case, I think we don't even have a way for that to happen because we've never defined anything 1 over coming out to be negative infinity. So this one is just straight up not possible. Our extended rules. Okay, so basically case 2 just never happens. So we don't have to worry about it. All right, and that's it. So we got that A or B is 0. That's what we were trying to show. So we are done. So I don't know, these extended rules are kind of fun. All right, let's move on to number 14, where we have to show that something is a subring. Definitely this type of question could definitely appear on the test, showing that something is a subring. So the easiest way to show that something is a subring, easiest way to show something is a subring is contained in theorem 3.6, which I have used so much that I actually have memorized what it says. But if you forgot, it is down here, theorem 3.6. For any subset of a ring, if it has these 3 properties, then it's a subring. So non-empty, closed under subtraction, closed under multiplication. Those are the 3 things you have to check. And that is the easiest way to do it. So we're going to show these 3 things. So we're going to show non-empty, closed under subtraction, and closed under multiplication. Okay, so for the first one, we just have to show that there's at least one element in this set. So let's look at what this set is. It's called the center of the ring. It's denoted C of R, and it consists of all elements Z in the ring such that ZR equals RZ for every element R in the ring. So in other words, this is the elements in the ring that commute with every other element in the ring. So first we have to think of just any element that has that property. Is there any element in the ring that always commutes with every other element in a ring? And we don't even know what ring this is, just some ring. So yes, there are always 2 elements that do this, and that is the multiplicative identity and the 0 element. However, remember, multiplicative identity, you can have rings that don't even have those because that is actually axiom 9, which means they don't all have it because only 1 through 8 are required to be a ring. So let me find where are these ring axioms. Yeah, so, oh, wait a minute, is it not number 9? Oh, it's 10, sorry, I misspoke. So not all rings have axiom 10, but they do all have an additive identity, 0, and 0 does commute multiplicatively because one of the properties that we have for rings is that, let's see if it's even down here somewhere. It should be, oh yeah, right here, theorem 3.5. Wait, why are these numbered? Oh, that's weird. I'm not going to worry about that. Why is this like 19 and 20 suddenly? It's not supposed to be like that. Is it? Oh, is it this? Okay, you know what? I'm going to fix that later. Anyway, okay, yeah. So like right here, the 0 element or the additive identity does commute with every element in the ring. Okay, so we could cite theorem 3.5 for that. Okay, so going back up here, C of R is non-empty, empty because 0 sub R must exist because I think that's like axiom 4 or something, and 0R commutes every element according to theorem 3.5. Okay, so now we just have to prove that C of R is closed under subtraction. So what that means is if you have 2 elements that are in C of R, their difference has to also be in C of R. So we're going to say suppose, I don't know, let's just call them A and B are in C of R. Our goal is to show A minus B is in C of R. Okay. So how can we leverage our assumption here that A and B are in C of R? Well, I'll just go back to the definition of what the C of R thing is. So A and B have to satisfy this statement right here in place of Z. So this means since A and B are in C of R, we know for all ring elements, so all R and R. So I'm going to place A in there instead of Z, so AR equals RA, and now I'll do it for B, so BR equals RB, and now we will show for all R and R. So what we want to show is that A minus B also satisfies this equation, so A minus B times R equals R times A minus B, but you have to ask yourself, why should that be true? Well, I guess coming from just these two equations, can we just subtract them from each other? Right? So this is true because we can subtract the two equations. That's not how you spell equations. You can subtract these two equations. And we get, maybe I'll just do it on like another line here so it's really clear. So it's going to be AR minus, so left minus left, right minus right. And then that's going to simplify if I factor out R, A minus B times R, factor out R. Be careful you don't assume things are commutative when you're factoring. So the R's here are on the right, then the R that we factor out needs to be on the right. The R's here are on the left, so the R we factor out needs to be on the left. And yeah, okay, so we've shown that A minus B commutes with R. Cool. Now for the last one, closed under multiplication, I'm basically just going to do the exact same thing. So we suppose that A and B, we suppose that A and B are in C of R, and we will show A times B is in C of R. And how can we do that? Well, we just have to leverage our assumption here about A and B being in C of R. So we get the same information as before. We get these two equations for any ring element R. And what we want to show is basically the same thing here, but using A times B. So we will show ABR equals RAB. Now, why should that be true? So this is a little bit less obvious. Why should ABR equal RAB? This is true because, I don't know. Let's write down ABR and see if there's anything we could do to it that would make it look like RAB. So I think actually there is, because don't we know that B times R from over here is the same as R times B? Right, so we could replace the BR part with RB. And then now when we look at it, we have AR, and we're also told over here that AR equals RA. So we can flip the AR part to become RA, and then the B stays in place. And now we have the whole equation, right? So we can use these two equations here. So basically like substituting from these, we get this three-part equation down here. Okay, that's pretty much it. Definitely we'll have something like this on the real test. Okay, the next one, number 18, prove that something is an isomorphism. Definitely we'll see one like this on the real test as well. Isomorphisms are really important. So we're going to let Q of square root of 2 is going to stand for this set. So this is basically what you get if you start with the rational numbers and you just throw in square root of 2 and you're like, I want to have the rational numbers, but I also want square root of 2. These are all the numbers that you would need to include to be able to add, subtract, multiply, or divide any rational number by square root of 2. So Q of square root of 2 is also a field under usual addition and multiplication operations, so just the regular real number operations. And we're going to define this function from Q square root of 2 to Q square root of 2 by this particular formula right here. So when you're plugging in anything in this field to the function, you have to identify which parts do not have a factor of square root of 2 and which parts are being multiplied by a factor of square root of 2. So it's kind of similar to imaginary numbers. In fact, it's like almost exactly the same as how imaginary numbers work, where you have a real part and an imaginary part. So we have a rational part and a non-rational part. And we're just flipping the sign between those. And we've got to prove that this is an isomorphism. So to prove that something is an isomorphism, just going to the identity of isomorphism, we have to do 4 things. So prove F is injective, or 1-to-1. We need to prove F is surjective, or onto. Oops, that's not what I meant to do. So prove F. Okay, Microsoft is being like this today. Prove F is surjective. We need to show the additive homomorphism equation. So show F is an additive homomorphism, and show F is a multiplicative homomorphism. Okay. So we're going to do these 4 things. First, prove that F is injective. Hopefully you guys have this definition memorized by now, and also the technique for proving it. So to show that something is injective, we assume that 2 elements get mapped to the same element, and then we prove that those 2 elements must have actually been the same. So we're going to let... so I'm going to look at 2 elements that are in the domain, but I'm not just going to call them A and B. I want to actually give them the form of what things in this set look like, which is this kind of 2-part thing. So I'm going to take 2 elements of this form. So A plus B square root of 2, and then for my other element, I'm going to use C plus D square root of 2. Kind of important to do this because otherwise, oops, you don't really have anything to... you could just call these 2 elements like X and Y or something, but then you would still have to expand them into this form in order to be able to do any math with them. So we're going to let A plus B square root of 2 and C plus D square root of 2 be in the domain, which is this thing. And we're going to go ahead and suppose that they have the same output from the function. So we suppose f of a of b square root of 2, oops, not f of x, f of this equals f of the other one. And then we want to show, so our goal is we will show that these were actually the same element so that these 2 equal each other. Okay, so that's the setup for proving injectivity. And we just need to, why is this X still here? We just need to leverage this assumption right here. Okay, so we're going to use that. So since we have this, maybe I should put this up here. Yeah, okay, so since we have that, we're going to go ahead and use the formula. So that tells us that, so f of a plus b square root of 2 is going to be a minus b square root of 2. I could have just typed it myself. Okay, and then f of c plus d square root of 2 is going to be c minus d square root of 2. All right, so we have to somehow use this to find that a plus b square root of 2 equals c plus d square root of 2. This is not that easy because, well, we don't have either of those things in here. We have a minus sign. And if we multiply through by negatives, we get plus signs in front of the b and the d, but not in front of the a and the c. So the technique you want to use here to show that these 2 are the same is kind of similar to what you would do for complex numbers. To show that 2 complex numbers are the same, you show that their real parts are the same and their imaginary parts are the same. We don't have real and imaginary parts here, but we do have rational parts and irrational parts. So to show that the rational parts are the same, we want to show that a equals c And to show the irrational parts are the same, we want to show that b equals d. But it's not that easy to get two equations like that out of one equation, unless you somehow know that certain parts of the equation cannot mix, so to speak. So what I want to do here is actually isolate the rational parts on one side of the equation and then isolate the irrational parts on the other side of the equation. Okay, and then I'll show you how this works. So I'm going to put a and c on one side, so I'm going to have a minus c on the left. And then on the right, I'm going to have b square root of 2 minus d square root of 2. So that's going to be b minus d square root of 2. Okay, and so now what I can conclude is, look at these two sides of the equation. The left side is rational, right? Because a and c have to come from the rational numbers. I guess I didn't explicitly state that, but I mean, up here I said that a plus b square root of 2, c plus d square root of 2 are in this set here. So the assumption then was that a, b, c, and d are rational numbers. Okay, because that's how the set is defined. So a minus c has to be a rational number. But what about b minus d? When you subtract, again, these are two rational numbers, so b minus d also has to be a rational number. So I'm going to write that down first of all. So since a, b, c, d are in Q, we know a minus c and b minus d are also in Q, because Q is closed under subtraction. It is actually a field. So then what we're saying here is something rational equals something rational times square root of 2. You know square root of 2 is not rational. It's one of the famous proofs you looked at in discrete structures, hopefully. So how can a rational number equal an irrational number over here? So the left-hand side is rational, and the right-hand side is irrational. Uh-oh. Square root of 2 is irrational. So how can this be true? This can only be true if actually the right-hand side was 0. So we had 0 times square root of 2. And then if that's the case, we would have also had to have 0 on the right for it to be, for both sides to be equal. So both left-hand side and right-hand side are 0. That's the only way we can get this right-hand side here to be rational. We know the left-hand side is rational, then the right-hand side has to be rational as well. Maybe that's the more correct way to say it. So the left-hand side is rational, then the right-hand side has to be rational, which can only happen if it is 0. Okay, so from that we get that b minus d equals 0, and that a minus c also equals 0. So b equals d and a equals c. So I guess kind of like what makes this problem work out is the fact that rational numbers and irrational numbers don't mix in some sense. You can like pull them out or like separate them from each other in a way. Okay. So that tells us exactly what we were looking for, which is a plus b square root of 2 is the same as c plus d square root of 2. All right, there's something kind of interesting about this. The way that the rational and irrational parts of these numbers behave kind of like orthogonal bases. Like if you have a two-dimensional space, you can separate every vector in the space into components multiplied by the bases that are orthogonal to each other. Irrational and irrational numbers in this one behave kind of similarly to that. You might be asking yourself, what if I put in square root of 3? Would that be like another thing I could use, kind of like a basis element? Okay, anyway. And then if you enjoy that sort of thing, you can get into Galois theory. All right, so let's look at proving that f is surjective. So to prove the function is surjective, we have to let ourselves take an element in the codomain and show that it has some corresponding element in the domain that maps to it. So we're going to say let y be in the codomain, which is this. And we will show there is some x in the domain, which is the same set, such that f of x equals y. So here you see I sort of blindly started out by just calling these elements by a single letter, but I am going to quickly actually have to expand them into like a plus b square root of 2 and c plus d square root of 2, because otherwise I can't really do anything with the formula. So I'm going to go ahead and let y be a plus b square root of 2. So y has to equal something like this, a plus b square root of 2. And now I need to figure out what would x have to be to map to this. So if the output from the function is a plus b square root of 2, what would the input have had to have been? Hopefully it's not that hard for you to figure out. It's just a sign switching function. So if the output is a plus b, the input would have had to have been a minus b. So basically you just go ahead and let x be, like you don't really have to do a solving process because it's pretty easy. So just let x be a minus b square root of 2. And then we just have to show that x is in this set, q square root of 2. And then that when we plug it into f, we do get y. So we know that x is going to be in q square root of 2. Oops, I'm supposed to put x there. Because y, it's defined as like any rational number plus any rational number times square root of 2. We said that y was in that set, so a and b must be rational numbers, so a and negative b will also be rational numbers. So how can I say it? Like a and b are in q. So negative b is in q as well. Okay. And then we just show that when we plug in x to the f function, we are going to get, it's just the sign switching function. So yeah, we should definitely get a plus b square root of 2. That's it. It's so easy. It's almost not even worth writing down. Okay. Now to show that f is an additive homomorphism. So we're just going to plug in, we're going to add two elements together. So like x plus y, and we're going to compare that to f of x plus f of y. But I think here I'm already doing it like the wrong way because I don't want to do single elements x and y. I want to write them in that expanded form where it's like a plus b square root of 2. Let me actually go ahead and do that. And I guess here I should probably say what my elements are. So like let me just copy it from up here. Let these two be elements in q square root of 2. And I'll just copy these again. Okay. Then I'm going to figure out what this is, and then I'm going to do the same thing separately down here, and hopefully these add up to be the same thing, because if they don't, then it's not an isomorphism. So for the first one here, I guess we kind of need to like simplify the regular part, the rational part, and the irrational part. So this is like a plus c plus b plus d square root of 2, like that. And then when I plug that into f, hopefully you can see what's going to happen. I'm going to get a plus c minus b plus d times square root of 2. And what's going to happen down here, why is that x still there? I'm going to have a minus b square root of 2 for the first part. And then for the second part, I'm going to have plus c minus d square root of 2. And you guys can see yourselves that this is the same, right? If I just group the a and the c together and the b and the d together, these are the same. Okay, so these are the same. So f is an additive homomorphism. Okay, and then I'm just going to copy and paste all this and put some multiplication signs in. Oh no! Put some multiplication signs in for the multiplicative part, because it is not much different. Okay, so boop, 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 boop. I need to do multiplication here instead of addition. Oh, this is going to be a little bit trickier, isn't it? Because I've got to multiply these. Okay, so yeah, this is going to be a little bit trickier. So maybe do some actual simplification here. And these are going to be multiplied as well. Boop, boop, boop. Yeah, that's going to be tricky too. Okay, let me do a little simplifying here. So first, outer, inner, last. Okay, so we're going to have, so for the rational parts here, I'm going to have, let me actually go ahead and do it. AC, and then when I do b square root of 2 times d square root of 2, that's going to be 2bd. So it's going to be 2bd. And then for the part that's multiplied by square root of 2, that's going to come from the outer and the inner terms. Why can I not get the square root of... Oh, okay. Okay, so the parts that are going to be multiplied by square root of 2 is going to be BC and AD, I think. So AD plus BC. So you see it actually turns out being really similar to what you get when you multiply two complex numbers. It's kind of interesting. Okay, so what I'm going to get out here is just all of this, but with a minus sign in the middle. So that changes to a minus. And when I do the down here part, I'm just going to, again, gather together the rational parts and the irrational parts. So the rational parts are going to come from my first and my last terms. So it's going to be AC, and then it's negative b square root of 2 times negative d square root of 2. So negatives are canceling, and that's going to give me plus 2bd. So that part's the same. Hopefully the other part is the same too. I'll just go ahead and put a minus there, hoping that it is. Okay, so what gets multiplied by square root of 2 is going to be the outer and inners. So minus bc square root of 2 and minus ad square root of 2. So yeah, it is going to be ad plus bc here. And these are the same, so f is an multiplicative homomorphism. Okay, so kind of time consuming, but not too bad to show that this is an isomorphism. Okay, so for number 19, prove that if f from z to z is an isomorphism, then it is the identity map. Okay, so for this one, you're going to need to rely on the fact that in an isomorphism, 0 always gets mapped to 0, and the identity, the multiplicative identity, always gets mapped to the multiplicative identity, and then you're going to need to use additive homomorphism property. Okay, so that 0 part and that additive, or the 1 getting mapped to 1 part is somewhere around, I was thinking, it should be somewhere around where we defined isomorphisms, right? So yeah, theorem 3.10, 0 gets mapped to 0. And yeah, part 4 as well, 1 gets mapped to 1. So if, yeah, so the identity of S is f of 1r, meaning 1s equals f of 1r. So we're going to cite theorem 3.10. Okay. That'll give us the first couple parts that we need. Okay. So, just realized I forgot to make things blue. Okay, so citing theorem 3.10. Theorem 3.10. We know that, so the identity in this one needs to be the identity in this one, so f of 1 equals 1. And the 0 element, same way, so f of 0 equals 0. Okay, so we can see it's at least the identity map on those two elements, but then how are we going to get like 2, 3, 4, 5, -2, -3, -4, -5, and so on? And so for that, I think there's also something, doesn't theorem 3.10 also say subtraction? Hold on. Yeah, so like a minus b, f of a minus b is f of a minus f of b. And then we have the same thing for addition, just coming from the fact that it's a homomorphism. Isomorphisms are homomorphisms. Okay, so then from the fact that f is a homomorphism, and theorem 3.10, we also have for any integers ab, we have these two equations, so f of a plus b equals f of a plus f of b, and f of a minus b equals f of a minus f of b. Okay, so how are we going to use those to get all the other integers, like what all the other integers map to, is the following. So if we just plug in 1 and... Sorry if you hear motorcycle revving. Somebody thinks they're really important out there driving past my house. So if we just plug in 1 and 1 for a and b, we get f of 2. Okay, so if I just plug in 1, 1, 1, 1, that is going to be 1 plus 1, which is going to be 2. So we get that f of 2 is 2. And basically from there on, you can just keep leveraging that property, and you could do like a complete induction proof. And for any integer n, if f of n equals n, then you can figure out what the next integer would be. So for f of n plus 1, you can do f of n plus f of 1, which is going to be n plus 1. Okay, so this is like your inductive step here, basically, without like fully saying that you're doing induction. But yeah, pretty much like if one integer maps to itself, then the next integer has to map to itself. So that takes care of all the positive integers, but for the negative ones, you can use this right here. So that takes care of all the positive ones. So for the negative integers, you can just plug in for a here with 0. Okay, and then you get that f of 0 equals f of 0 minus f of b. So that means f of negative b is going to be negative f of b. And since you already know that for any integer, it's the identity map when the integer is positive. Okay, so that's going to be basically just negative b. All right, so f of negative b equals negative b when b is positive. Positive. Okay, I feel like this is a little bit sloppier than the version I did in the original solutions, but I'm getting a little bit tired. So let's go ahead and let me just actually do one more because I am getting a little bit tired. I'm just going to do 22. So this was 22. It's a little bit harder than 21, I think. All right, so prove the following for any field f and for any a of x, b of x, and c of x in f bracket x, if a of x divides b of x times c of x, and a of x and b of x are relatively prime, then a of x divides c of x. Okay, so this looks like a universal conditional statement, so I'm going to try using a direct proof. So in other words, I am just going to assume I'm going to start off by turning my for all or my for any into a let. So I'm going to say let f be a field, and let a of x, b of x, c of x be in f bracket x. So I'll just copy that part. It's blue. Okay, and then I'm going to go ahead and assume the if part. So assume everything after if until the word then. Okay, so just copying that. And then we will show, and that's going to be this part. Okay, so let me look at what I have here and think about it a little bit. So we're assuming this. I can get one equation from this. And we're also assuming a of x, b of x are relatively prime. There is an equation I can write from that, that they are a linear combination of a of x and b of x equals 1. And then I want to show this divisibility so that I can do that with an equation. So when I want to show that a of x divides c of x, I basically need to be able to factor c of x and see that a of x is a factor of it. So in other words, like note to self, want to factor c of x and see a of x as a factor. Okay, so that is my goal. And now let me use my assumptions. Okay, so since a of x divides b of x, c of x, just using definition of divisibility, Definition of divisibility for divisibility polynomials. There is some, let's call it, I don't know, d of x in the same polynomial ring such that, so basically same equation that you get for integer divisibility, the thing being divided equals the thing doing the dividing times some other factor. Okay, so this is going to equal a of x times some other factor, which I'm calling d of x. All right, so that's one equation. Now from my other assumption, a of x and b of x being relatively prime, we do have a version of that whole linear combination thing for polynomials. Can't remember what number it is, but let's see if we can find it down here somewhere. Relatively prime. Well, we do have the whole thing that we're trying to prove here. It's just a theorem, but don't... If I ask you to prove one of these theorems, you better not cite that theorem as the proof. Okay, I'm asking you to produce the proof. Okay, so GCD... yeah, this one, theorem 4.8, is about writing the GCD as a linear combination of the two polynomials. So the other factors here, we can call them u of x and b of x. Okay, so we're going to cite theorem 4.8. Okay, so coming back up here. Nope, nope, too far. Okay. From theorem 4.8, we know there are, so we're going to call it, oops, okay, I undid my typing somehow. From theorem 4.8, we know there are, so I'm going to call them u of x, b of x in f bracket x, such that, so the GCD when relatively prime is 1. So what we get is that 1 equals this linear combination of a of x times u of x. Oops. See, my thumbs are getting all fumbly, and that's why I need to stop after this problem. Okay, b of x, v of x. Okay, so at this point we have two equations, which is great, and we're trying to show one equation, so we want to factor c of x and see a of x as a factor. So basically, like, I need to somehow get c of x by itself and have a of x as a factor, but this is a little bit like, not exactly clear on how I'm gonna do this. It looks a little bit tricky. So how can I get c of x by itself? Because I can't like factor out, I mean, I can't like divide through by b of x, but I must be able to do something kind of clever. I wonder what that is. Okay, so I know I can't divide through by b of x, but I really want to get rid of this b of x here, right? So a lot of what you do in math is motivated by like really wanting to get rid of things or change them, make them look different. I want to get rid of that b of x. I wish that I could replace that b of x with a 1. I would just love to replace that b of x with a 1. And I can't do it directly, but when I look at this other equation, I'm like, well, here's b of x, and here's a 1. I wonder if I can make any hay with that. It's honestly like kind of a dumb idea, but that's kind of where my brain goes. So I'm thinking like, I really wish I could just replace this. I could like have b of x be equal to 1, but it's not, right? Because like, first of all, there's v of x is down here, and then there's also this other a thing in here, which is like not great. But okay, so I'm like, well, I don't know, maybe somehow there's a 1 here, so like maybe I can't even replace b of x from down here because I can't solve this for b of x. But if up here I had b of x, v of x, then I could replace that with 1 minus a of x, u of x. Like maybe that would be better. It would be closer to 1 somehow. So that's kind of like where my brain is going. So I'm thinking, okay, I wish I had b of x, v of x, but I can put a v of x in there by just multiplying through. So what I can do is multiply through this one by v of x. And then I would have, I'm going to put the v of x in the middle here. I'll put it on the end for this one. Okay, because then I have v of x, right? And then I could replace v of x here. Okay, so then like solving this one. So solving for v of x, you get b of x equals 1 minus a of x u of x. Okay, and then multiplying through by v of x, we get that. And then replacing, so with substituting, this becomes, so I'm going to replace b of x with 1 minus a of x u of x. Okay, so like my goal here was to get 1 times c of x, and it didn't exactly do it, but I got like 1 times c of x plus, or like minus some other crap, so I kind of got closer to having 1 there. Do you see what I was doing here? Hopefully. So at this point, you're like, okay, how close am I to the goal? I want to factor c of x and see a of x as a factor. Well, actually, we're like really close because here's some, this has an a, and this has an a. So if I expand this, I get c of x minus a of x u of x c of x. And now I know you're thinking like, but to isolate c of x, we should put all the c of x factors on one side because that's the way you usually solve. But actually, because we're trying to factor c of x and get a factor of a of x, we can just kick all of this whole thing to the opposite side and factor out an a. So we're not like solving and isolating all the c of x factors, but we are getting a factor of a of x out of all of them. So I put that on the opposite side, it becomes positive, and then I still have this part. And then I can factor out a of x. So actually, this completely bonkers nonsensical idea of wanting to replace b with 1 pretty much worked out. And that is how a lot of math transpires. So d of x, d of x. Okay, so you see here I have a factor of a of x in c of x, because the rest of this stuff is a polynomial in f bracket x. Okay, so by definition of divisibility for polynomials, a of x divides c of x. Okay, that is what we wanted, and so we are done. And that is the end of this review. Hopefully it helped, and send me an email if you have any questions.